Hey guys, I hope you're as excited for this week as I am. This is where the course really starts ramping up. Um, from here on out, what we're going to be doing is we're going to be looking at relationships between variables. We're going to be looking to see if we can take one variable and predict another variable, some sort of outcome with it, which can be really powerful and insightful and fun. But I'll admit I'm a little bit biased there. The first analysis we're going to look at in this phase of the course is a chi-squared analysis. But before we get to that, let's talk a little bit about what it means when we're analyzing relationships between variables. So whenever we're exploring variable relationships, we're at least going to have two different types of variables. There's going to be at least one input and an output. The idea here is that we're testing to see if the input variable can significantly predict the output or some type of outcome. So we could look at, for instance, if someone's height could predict their weight. Is there going to be a relationship there? So the taller a person is, does that lead to, on average, an increase on how much they weigh? You could also look at, say, for social media, for instance, the amount that you pay your input on a social media ad, does it lead to an increase in views or website visits? You could look at, okay, ad A or ad B. These are going to be my input, which ad they saw. And you could go and test, does that lead to higher purchase intent or higher willingness to pay for that product? Oftentimes the idea with an input is that the input is something you have some kind of control over. And so you say, okay, if we shift this or we make changes in our input, can we then produce significant changes in our output? So another example, let's say that we have two different logo designs and we want to know, okay, if those who see these logo designs, does it lead to how much they're willing to pay for this product, how much money they're going to put forward to buy a Blitz Blend shake. Now, when we're looking at this, say we run a survey like we've been doing, and we see that the average amount they're willing to spend for the logo design on the left is $5.32. But the average that they're willing to spend for the logo design on the right is $5.72. Now, anytime we run any test, there's going to be differences. So for instance, in here, like we have a very, very low likelihood that this willingness to pay is going to be the exact same on average for both logo designs, like a $5.32 for both. That's just not going to happen. There's a lot of noise. There's a lot of randomness. And so when we're looking at a relationship between an input and an output, it's really important that we try to figure out, okay, how much of this is due to chance, to randomness. You know, we want to know, like, how reliable is this test? If I ran it again, would the Blitz Blend on the right, that logo, would it still come out on top? Is that like a reliable finding? Or is it completely random and every time I run the test, one ends up being first and the other second, and it's just kind of a flip of a coin as to which one ends up on top? Let's take another example really quick. Let's say that you and I have a little contest, and let's say that you take a coin and I take a coin, and we both flip it 10 times. And I come up with 7 heads, and you come up with 3 heads, and the goal is to get the highest number of heads. And since I won, evidently I'm better at flipping heads than you are. And we can go with that. And if we had to choose a champion to compete in Norway or something like that, I would be the one because I'm better at flipping heads than you. So obviously that's like ludicrous because it was just random chance that I ended up flipping more heads than you. It wasn't reliable. The next time we went, you could easily win or we could tie. Who knows? It's just due to chance. And so to help us understand whether or not a relationship like who flips a coin and the number of heads that you get, a relationship between those two variables, in order to know how much of it is due to chance, we have something called a p-value. Now, I know that you've dealt with p-values in the past, and it's something that very few people can still define, and that's totally fine. We're going to look at it in a more simple light. This is a simple definition of a p-value. It's the likelihood that a relationship between like two variables, like your input and output, is due to chance or random. And this p-value that we get is always going to be between 0 and 1. And if we flip that into percentages, 0% and 100%. There's the likelihood that it's going to be due to chance is going to be somewhere between 0% and 100%, or 0.000 and 1. So let's take into account the coin flipping. What's the likelihood that me flipping more heads than you was due to chance? You know, we'd probably see a really high p-value if we did a bunch of coin flipping contests and added them all up and averaged it all up and ran a test. We'd see probably a p-value of, I don't know, 0.87, which would be an 87% likelihood that any differences in how we perform in flipping heads is going to be due to chance. So to break this down a little bit, statisticians have given us this kind of magic number, which is 0.05, a 5% likelihood that it's due to chance. And they said that if it's lower than that, if it's lower than a 5% likelihood that it's due to chance, then we're going to consider that significant. So looking at this little number line here, where we have 0 and 1, if it's somewhere here between 0 and 0.05, that's significant. Furthermore, if it's not quite below 0.05, but it's below 0.1, it's between those two, then we'd say that that's marginally significant. Not quite significant, but marginally, it's getting there. These are like the magic numbers for when we're doing academic research or things like that. But in the real world, I would just always try to take this into account. What is the likelihood that this decision that we're making is due to chance? If it's like $1 million decision, you want to make sure that likelihood that it's due to chance is very low. You would want that to be significant. If you make the wrong decision and it costs you $100, $10, I don't know, then maybe you're like, okay, you know what? If there's a 40% likelihood it's due to chance, I don't know. We'll gamble it. I don't really care that much if we made the wrong decision. And so in real life, there isn't really necessarily like a magic significant number. It's how much risk are you willing to take. But for this course, just to help us kind of gain traction with this idea, we will be defining significant as something less than 0.05, but marginally significant is something between 0.05 and 0.1. So between a 5% and a 10% likelihood of being due to chance. Now, most students struggle with this idea because we're used to bigger numbers being better. But remember, for p-value, it's the opposite, okay? For p-value, if it's the bigger it is, the higher likelihood it is to be due to chance. The smaller it is, the lower likelihood it is to be due to chance. We don't want chance to be involved when making decisions. We want to limit it as much as possible, and that's why a lower p-value is ideal. So let's go back to this example with logo designs, and let's say that when running a test between logo design and how much they're willing to spend, you find a p-value of 0.02, which means that there's a 2% likelihood that difference between how much they're willing to pay for both logo designs is due to chance. Okay, so that 2% likelihood of being due to chance, that's nice, that's significant. That's something I'd feel more comfortable making a decision on. We could say, all right, let's go with the logo design on the right. However, if we had a p-value of 0.87, then the difference between the two, there'd be an 87% likelihood that difference is due to chance. And that's really high, definitely not significant. And so what we do in these cases is, I know this is going to be really hard to kind of get in your head, but we would treat it as a tie. Yes, there's a 40-cent difference between the two, but because that difference has a high likelihood of being due to chance, we're going to treat it as if it was a tie. It'd be like if you had two nearly identical runners and they competed in a race, and runner A won the first time, but then they're so similar that they run a race again, and runner B won the second time, and it just continues on, and it was like 50-50 shot as to whether runner A or runner B would win. and you were asked who's the better runner. You don't know. You can't really base it off of their races. They seem pretty comparable because it's like a flip a coin. Who wins? It's highly due to chance. So we can't determine who the better runner is. That would be the case here. If there's an 87% likelihood that this difference is due to chance, next time we run a test on these two, the logo design on the left might be higher. They might be tied. Who knows what it is? We can't determine which logo design is the better logo design because that chance is too high. And so we treat it like a tie. However, in cases where the p-value is significant, then you can determine, okay, it looks like the logo design on the right, people are willing to pay more for that. Let's go with that one. And I would include as well something that's marginally significant. So if the p-value is not quite below 0.05, but still below 0.1, then yeah, that's something we can go off of. We'd say, okay, there is a marginally significant difference between these two. Let's go with blitz blend on the right. So now that we've covered this, we now understand that, okay, we have an input variable and we have an output variable. The p-value tells us the likelihood that that relationship is due to chance. But when do I run a chi-squared analysis? What does that have to do with anything? So before we get to chi-squared analysis, let's just refresh on what we covered last week, where there's two different variable types. You have categories and numbers. Categories are just like you're labeling things, but numbers is more of like a measurement. Simply put, we're going to run a chi-squared analysis if our input variable is a category and our output variable is also a category. Okay, so we're going to test with the chi-squared if shifts in our categorical input can significantly predict changes in our categorical output. And so for the assignments for this week, we'll continue learning about chi-squared analysis by running different chi-squared tests.